mass matrix times z double dot equals b theta theta dot plus the Jacobian of point C1, and I'll draw the figure again. See if you've forgotten, J C2 transpose F C2, and that was for this figure C1 C2 H. And remember, we said X, Y is the position of C1, theta 1 was this, and theta 2 was that. Okay, so theta here in this equation is referred to basically theta 1, theta 2, and the rate. So that B is going to be dependent on the angles. Okay, so what we are now trying to do is we are trying to understand what happens when, so what is really foot strike? So remember, I draw the caricature that the black is the stance leg. Sorry, the black should be behind. So let me draw it this way. And then let me draw the red one to show the swing leg. So this is just before this, just before collision. What I now need to do is I need to figure out what will happen after the red line or the swing leg has collided. So now it's touching, here it's not touching. Just after collision. So here's something we want to note, which is this is still C1, which is the leg anchored to the ground. This is C2. This is C1. This is C2. The way you differentiate these two phases is that just before the red or the swing leg hits the ground, C1 is at rest, right? It is anchored to the ground. When collision does take place, this point, the foot of the swing leg anchors to the ground, which means now the velocity of C2 is 0. Okay, so there's a difference. C1 is 0 in the first case, C2 is 0 in the second case. And that's why you will see there will be a sort of a jump in the velocities. By jump, I mean the velocities will suddenly change. The positions won't change because the position they're connected, but the velocities will jump. So think of you're walking, your foot hits the ground, you feel a jerk in your body, and that's because your one foot has come to rest, the one which was swinging, and the other one is now free to swing back. So what we do in this world is we denote the instance before foot strike or collision as minus. So it's the tiny instance before collision takes place. So I'll say that VC minus is equal to 0. And then the instance just after collision is usually denoted by positive. And we do that only because the time, we assume that the time is does not change between this collision. So the collision takes very, very fast that you don't really see a change in time. That's why we write minus and plus. So minus is denotes before collision, and then plus denotes after collision. So if I might remind you, when we talked about bouncing ball, we had the same thing where there was an instant just before the ball hits the ground, that's minus. And then there was the instant after the ball hit the ground and reversed its direction, that's plus. And that instant is very short. It's in reality, it should be maybe a millisecond, but for modeling, we just ignore it. We don't say that time has actually changed, okay? Okay, so with that, let's do one thing with these equations, which is let's take this equation and let's integrate it from the instant before collision, which you can, in the limit, you can call that as t minus and this as t plus, where really t minus and t plus are separated by almost nothing, almost tending to zero, almost tending to at the same time. So let's integrate these equations. Mz double dot equals b theta theta dot plus jc1 f jc1 transpose fc1 plus jc2 fc2, and I should put dt's everywhere. So t minus to t positive, t minus to t positive, t minus to t positive, t minus to t positive. Okay, it's the same equation, just that I integrated it. You can see it here. Okay, now here are a few assumptions we make, and these are, and see if this makes sense. So first, we assume that the term due to Coriolis acceleration and centripetal acceleration, good catch, transpose of JC2. That's right. Thank you. We assume that the centripetal, so those don't quite change in this tiny instant of time. They almost are, the change is negligible. So, and that's like an assumption and it's found to be true. So we'll ignore that term. Okay. Now, when we integrate this term, the first term, we end up with jc1 fc1 dt. Fc1 dt, this term here, is nothing but the impulse at c1. Okay, so c1 is the training leg. So imagine you're walking, there is an impulse which comes on the front leg and the back leg. So impulse at C2, impulse at C1, that's FC1 dt, FC2 dt. Now, we'll make this assumption that when the foot hits the ground, the impulse is felt at C2. This is the leg which is in front. Okay, so if you walk, you can think about this. Which leg will feel an impulse? It's usually the front leg. So for these walkers, so when you are walking, when humans are walking, there's an impulse on both legs. It's because both our legs stay on the ground for an extended period of time, which is called double stance. But for this machine, which doesn't have feet, we can assume that this impulse, the impulse on the trailing leg C1, which is the rear leg, is equal to 0. So we'll ignore that. Okay, so it's also been found that that's true. So we'll only keep this impulse intact. So let's call this impulse as, let's see, what notation did I use? Just call it P. Okay, PC2, which is the impulse. So now what I can do is I can write this as mz, the integral of z double dot, which is the acceleration with respect to dt, is going to be the velocity. So I can write that as z dot with the positive sign. This is at t positive minus z dot negative. This is for instant t negative, equals, first term is 0, the second term is 0. We're only left with, so the integral fc dt is pc2. So it's jc2 transpose pc2. So since jc2 is, which is basically the configuration of the system, j is dx, dx, d theta, and so on, that doesn't change with time because the configuration doesn't change. We can pull that out of the integration and we are left with integral fc dt, which is pc2. So this is our expression for what happens during foot strike. And this was pretty simple because with the pains we took to derive the equations for single stand. So with this, we can now proceed to get the derivations, but we're missing one thing, which is we've still not enforced the condition that the velocity of C2 is zero. It's not shown up in these equations yet. So let's just state that, and that will be pretty simple to do because we already have um, understood what Jacobians are. So the velocity of C2 positive is going to be the Jacobian of C2 times Z dot positive, right? So that's the definition of the Jacobian. So what we have is this is equal to 0 because the front foot comes to rest. And so we have, this is equation 2. I'll write the first equation which I wrote down earlier back here. So m z dot plus minus c dot negative equals j transpose c2 p c2. We can write this as mz dot plus from previous page. So equals, let me move the C2 on the left side because I don't know what that value is, but I'm going to find that. Okay, so let's take one, let's call this 1A. So now from 1A and 2, we can write M. So M times Z dot positives, that's the first term. And then we need to write this one. So I'm going to write MPC2 times JC2. So it will be here with the negative sign equals mz dot negative. So this takes care of equation 1a. And equation 2 is basically jc2 z dot equals 0. So that's going to be jc2, which can multiply with z dot plus, and then 0 for pc2 because there's no term here involving pc2. And then I'll need to put a 0 here. So this is my equation for the foot strike. Okay. Any questions so far? So this is the most complicated it gets. There's no more complications than this one. It's pretty much algorithmic. There's nothing much in terms of you got to think. You just have to keep writing the equations in the right way. And since I wrote this down, I'll show you. You can actually automate this, and then you can use that code to write equations for more complicated systems. It comes out to be the same form as long as you can identify this m jc2. You can always write this in this form. The m and jc2 comes from the earlier part, the Euler-Lagrange equations. Okay, now a few things which I'm missing, and I'll do this, and then I'll show you the derivation, which is, so number one is detect collision, right? I said between going from single stance when the leg is swinging to the instant where there's a foot strike, you need to ascertain when that instant is going to take place. Like for the ball, it was when the ball reaches the ground. So here is a caricature of the two legs. Let me draw the other one with red. So this is when the foot has hit the ground. Let me call this angle theta 1, and then the other one is theta 2. So we detect collision when basically the two legs are in the way they've shown. It's basically a triangle with these two sides are equal. So we would have the condition that, so if this is theta 1, then we can see that this is, maybe I should have just make it slightly bigger. Okay. Okay, so now you can see that this angle here can also be written as 2 theta 1, right? Because this is theta 1, so that's going to be twice that. And so the condition for collision is that theta 2, which you can see here, equals minus 2 theta 1. And why is there a minus sign? Well, you can see the direction of this arrow. This arrow points clockwise, counterclockwise, while this arrow points clockwise. And that's why I need to put the negative sign. So in other words, this is theta 2 plus 2 theta 1 equals 0. So when this condition is met, we do detect collision. The final piece which is left is to actually swap legs. So what we do here is, instead of trying to simulate so to say 2 steps, which is really what it is, right? You're on your right leg, and then the leg hits the ground, and then there's a phase when the left leg is on the ground and the right leg swings, and then again the right leg hits the ground. So in two steps you'll have the right leg on the ground, and that's an easier way of thinking about walking. But to make our life easy, instead of doing this for 2 steps, we only do it for 1 step. So we essentially swap the legs. So after 1 step, so left leg swings, it hits the ground, it becomes the stance leg. Instead of keeping it that way, we change the roles of the left and right. So we only have to simulate 1 step, and then we can just repeat it. So that requires us to do some renaming. So question: is the trailing leg still in contact with the ground just after the front leg strikes the ground, or when does the swing of the trailing leg begin? So when you don't have the assumption here is that at any point of time only one foot is on the ground. So when the front foot hits the ground, we assume that the back leg has left the ground. And the way we ensure that in the modeling is by saying that the impulse on the trailing leg, which is PC1, which I wrote down on the previous page, is actually equal to 0. But if you had a more complex model with foot, knees, then you might not want to make that assumption. Okay. So now swapping of legs. Okay, so this is the instant just after collision. Okay, I denoted by positive just to indicate that it's after collision. What we are doing now is we are swapping the legs. So we want to make the red leg become the black leg, or the swing leg, which is red. We want to swap it with the black one. So the configuration is the same, but we want to rename this angle as theta 1 and this angle as theta 2. And since this is the in clockwise, I'll call that negative. Negative should be here. So this is just after foot strike, and then this is the swap. So what we need to do is essentially look at the two figures and swap the angle. So it's easy to see that theta 2 here equals, okay, my bad, this should be theta 2. I need to just keep it theta 2 because when I swap it, I won't swap it as the angle is still theta 2, my bad. This should be, this is in the direction shown, and which is clockwise, and here it's shown as counterclockwise. So all I need to do is put a negative sign so that this angle theta 2 on the right side of the figure corresponds to on the left. And then for the theta 1 swap, you can see that here is this is the angle between the vertical and the black leg. This should be the same as this angle here. So I can write this as theta 2 positive minus theta 1 positive. Well, that's not right. So this theta 1 positive is clockwise. So first I need to switch it. So it's theta 1 negative. And I did that because now the arrow, you can see it points out in the clockwise direction. So now this angle is going to be theta 2 positive minus all this minus this. So minus theta 1 positive. So in general, it will be theta 2 positive plus theta 1 positive. So eventually I have theta 1 equals theta 1 positive plus theta 2 positive. So once I do this swap, I can now continue integrating equations in this sense. Okay, that's enough theory. I'm going to show you how to derive this in Matlab. From the double pendulum, which I talked about. So many things here should appear the same as that in double pendulum, except that I need to add the equations for foot strike, which was not in the double pendulum. So define all the symbolic variables. To do the Euler-Lagrange, I define position vectors. These are vectors, the rotation matrix is exactly like the ones I wrote down on paper, so I will not go through them. The velocity we saw is simply taking the Jacobians of different points with respect to um, theta 1, theta 2. So there are 4 variables, x, y, theta 1, theta 2. Unlike the double pendulum where you only had 2, theta 1 and theta 2, because it's a floating wave system. So I will not spend time there. We also need to find the positions of the center of mass with respect to global frame. So this is with respect to the ground, right? And so that I need to get the rotation matrix, which takes the ground frame to the frame attached to the ramp. The kinetic energy is exactly the same as the double the double pendulum. Okay, once you get the energy TV, you can get the Lagrangian, and the equations of motion come from Euler-Lagrange. And here, what I did was to the double pendulum, I added 2 more variables, x and y, corresponding to the floating waves. So now I would have to write 4 equations, copy pasting the same formula, except that I need to add these 4 states. So far it's all follows from the double pendulum. Then we take, to find the A and B matrices, we take the Jacobian, okay, and then do a bit of simplification, and we end up with the matrix. So this is almost everything here flows from the double pendulum, except for the fact that these give me 4 equations. And as I said, we don't really require the four equations. We don't require the first 2 equations, because those equations just express the fact that one of the point is anchored to the ground. So I only have to look at 2 of the 4 equations, which are basically buried in the 2 by 2 matrix embedded within that A matrix. And that's what I've collected. So A is something like this. There's an entry here, 2 by 2, 2 by 2, 2 by 2, 2 by 2. So this is ASS. So I'll write it as ASS. And this A matrices are from here, A. Where A equals A11, A12, A21, A22. Okay, so this might make it slightly more clear what I'm doing. This ASS has a 4 by 4 matrix, but what I'm interested in this element, which gives me A11, A12, and that's what I wrote down over here. And same for B, it's just this last 2. So once we get that, we get the equations for single stance, then we have to find the equations for foot strike, and then I need to get this Jacobian. So JSW I denoted as Jacobian of C2, and JS, another one. Yeah, so in this case, I only need the Jacobian of C2. That's, I don't have the Jacobian for C1. So I wrote that down here. And then couple of simplifications, but eventually I uh, have to write this equation AHS BHS, which is basically the formula. Maybe this is the most clear one. So what I'm trying to do is write this down. This is the formula from today's notes. AHS is this, so if we write it this way, maybe it's more clear. Okay, this J is JC2, and this ANHS is basically the N. So run this. And then it spits out all the various terms. So there are two parts to it. Once you get these terms, you need to copy paste them in certain places in the code. So for example, this part, which is giving the equations for single stance, I take that, I copy it in the simulator where I have the single stance right hand side, which is okay right here. So copy paste it from this. So I just have this over here. And then the second piece, which is J's, that goes in the place which has foot strike. It should be here. Copy paste it from derive. So it's in foot strike. So that's where the other part, here you can see this, it's copy pasted. Okay, so everything, if everything works right and you've got all that together, you need to initialize the system, the walker. In this case, I decided to give, so I should maybe put this Q1 is a slightly different notation I use. This is really theta 1 and U1 is theta omega 1 and so on. Okay, so I made some guesses and I simulated it, and I also have animation going. Huh, it didn't show up. Let me see. Oh yeah, okay, so let me uncomment this, my bad. Okay, so it's simulated. So this is what happens if you try to give some naive initial condition. Okay, just failed. Okay, and that's because really when you want these machines to work, you want to launch them the right way. And those are some videos I did not show, but launching them right is a big challenge. I'm going to change this initial condition. Let's just change it to 0.3 and see what happens. So you got to sort of guess. Okay, so this one looks slightly better. Looks like it's walking, but looks like it will fall eventually. Okay, that's not bad. Let's try more steps. Okay, that worked well. So maybe that's a good guess. Here, I actually knew the guess. I actually knew that 0.3 would work, and that's why I put it. But if you naively try to do something, it'll actually